Good afternoon. Good afternoon, Katie. Good afternoon, Emily. Oh, I see why I can't see. Hold on a second. I can't see. Good, okay. Good afternoon, Chris. Good afternoon, Yavi. Good afternoon, Maria. Good afternoon, Cheska. Good afternoon, Michelle F. Good afternoon. Good afternoon, Freddie. Good afternoon, Jada. Good afternoon, Stephanie. Afternoon, Maria. Good afternoon, Marilyn. Good afternoon, Michelle F. Afternoon, Michelle. Oh, Michelle Quach has joined. Okay. Good afternoon, Yavi. Good a Oh, they're like more and more people are joining the no adjective club. Interesting. Maybe they were always there and I didn't know. Good afternoon, Shy. Good afternoon, Brooke. I think someone else is here. Wait a minute. Did someone else just come? Sorry. Shy. Oh, they're Shy. All right. Hello. Uh, wait, I feel like I missed somebody, but okay. Felix, if I missed you, I said Jada. Okay. Good. Hello, everybody. Okay. Um, oh, yes. Oh, which what, you have a live Eevee? Like you have an Eevee that's, I'm not sure what they mean. Like you have like a creature who's named Eevee or like, oh, yeah. Oh, Pixelmon. Yeah, Pixelmon, the best of all worlds at the same time. That's, okay. Oh my God, Michelle F. Whoa. Okay. Yowza. Look, honestly, it's a skill even to know how to get Pixelmon like uh I don't even remember what the word is, but like oh the weeks of stress trying to even for me to even figure out how to get Pixelmon. It made me feel so stupid, but yeah, we eventually got it. Okay. Well, because you have to, I know. Oh, come on. She's saying, come on. Yeah, server, right. Like getting those servers. Oh, I mean, I learned it all with my older son, and he used to actually come to John Jay classes, and then John Jay students would show him how to get servers. I mean, this is a long time ago, like before COVID, and I was like, what is going on? And then by the time I got to my younger son, I thought I could, and I now I do it, but like, oh, you have to freaking with the go into the anyway, all right. Yeah, Forge, right. Forge. Oh my God. All right, sorry. Like I feel about Forge the way a lot and all that stuff, like the way a lot of people feel about physics. I mean, I get it. Like I get why it's worth it, but oh, okay. Wait, oh, yeah, wait. Oh, did I call it? Wait a minute. Oh no, thank you, private chat person. No, I did it wrong. Okay, hold on. I knew I was doing something wrong with the game turns. Hang on one second, please. There's someone in the private chat who's pointing at. I think I missed yesterday's. So I posted today's. I called it. This keeps happening. I could have sworn I called it. Wait. Oh no, the one I posted yesterday was to the wrong. All right, hang on a second. I see what happened. Ay, ay, ay. No wonder. All right, bear with me, everybody. Thank you, private chat person who. How did that happen? Yeah, no. All right. That game 10, thank you. Okay. There was a game 10, a game turn 10 that was posted. Yes. What in the name? What did I do? That was supposed to be. Oh, yeah, yeah. Oh my God. Hold on a second. Yeah, yeah. But it's all messed up. I might not even be able to fix this right now. The Oh, I see, I see, I see. Oh, wait, no. Okay, okay, okay. I see what happened. So the game turned yesterday. Thank you again. The person who's just putting this in the game turn that was posted yesterday. What in the name? No, I don't see. Should have been game. I'm so confused. Oh my God. Hold on. Some I feel like that came from the other class accidentally. All right, I'm just gonna get rid of it. I don't, but that does mean you were missing a game turn 20, right? Which so I did give you a game turn on Monday. And someone's here. Sorry. Okay, this is not the way I meant to start class today. But it's not your it's right. Maybe you're right that today is supposed to be 20, and that would make a lot of sense, except for one thing, which is that everything else was 20 yesterday. Like the class video was 20 and the class notes were 20. That's what's so something I did something wrong somewhere. Oh, good heavens. All right. So, and I know this is like not the most important issue of the world, but it is confusing. No problem. Private chat. I mean, the other private chat person. Okay. But I gave you a game turn on Monday, and I'm giving you a game turn today. There's something wrong with the numbering. It's a little bit messing with my head. It may be messing with your. There is something wrong. I will try to fix it. I don't know. Something is wrong. But hopefully you had one from yesterday, from Monday, and hello, Shawnee. Good to see you. Okay. Thank you for pointing it out. I will try to think of this. Something went wrong when I tried to fix something in the other class, I think. But okay. All right. Um, uh, so as you can see, I'm not operating on, I am not firing on all cylinders. So I'm going to try to go back to physics where it, at least, no. And the private chat person who pointed out, you did not create the confusion. Right, bold of me to assume that. No. And look, I know a lot of you. I know this is not like this. Some of you don't lose sleep over the person that pointed this out. They are not should not be sorry. They did not create confusion. There was an error. I'm glad it was pointed out, and it just I created confusion. I'm now realizing that the error is like bigger than I thought. So but I'm not frustrated that the person pointed it out. No, and it's good. I mean, no, and I know it's nice to keep track of like what class we're on, but okay. But I'm gonna go back to physics. Uh, and I'll try to fix that. Okay. Hello. And are we? Okay. I'm gonna go back to the thing that I would have done yesterday. Um, if I could summarize it really with the Doppler effect. I would like to finish this today, and I'd like to move on to electricity. I don't quite know how we're gonna do both today. We probably won't, but um the thing about the Doppler effect, it's like important. It's really important. Um, it's I spend a lot of time on it every year because on the one hand, it's a type of problem that I think everybody can solve if they practice it enough, solving all four cases. I think everybody can get it. And when I mean get it, I mean not just with that equation that you saw in lab. I think it's within everybody's grasp to see how to solve one. And I think it's worth the computation. But then I also think once you can solve all the four cases of a Doppler effect, there is an observation that can be made when you look at the number that you can sort of only see if you see all the numbers at the end of a Doppler effect problem, if you compare all four cases, or at least if you cross compare pairs of cases. It shows something very, very important and sort of surprising about waves. That's what I want you to see. And to be super honest, I mean, I know apparently I'm definitely off right now, but to be like, they're usually one of the problems on the final exam is usually a big Doppler effect problem. That's usually a choice. Like not everybody necessarily does it, but a lot of people do because some of the other choices maybe are harder in a different way. So it is. So I'm not just spinning your wheels. It's like it's worth knowing what's going on behind these Doppler effect problems. Um, so, so what I want to do is, I'm assuming you, please tell me in the chat, please confirm in the chat. I think in front of you in this class, like last Wednesday, I think I actually walked through the procedure for doing one of the four cases. And then I asked you to do the rest with different numbers, perhaps for homework. Is that correct that I walked through one? I did case one. Okay. Thank you, Katie. Okay. That's what I thought. Okay. So, what I'm going to do now is like briefly, quickly review like how I did that. But I'm going to show you what then if you do that exact same thing for all the other three cases, what numbers you get, and what they mean. So hang on one second. I just have to get that. Now, if you don't mind, also Katie or someone else. So I'm going to like, so okay. If you could remind me also in the chat, the number that I did for case one, was it the exact numbers from the homework sheet, or was it made up numbers for the class period? Or could you give me the numbers? In other words, what was the frequency of the wave according to the source in the one that we did in class? If anybody could tell me in the chat when we did this in class on last Wednesday, can you tell me what was F sub W S? Oh, is it there? Oh, okay, okay. Oh, it was. Okay, great. Thank you. That makes sense. And actually, there's one other number I'll want. Oh, yes, of course it would. Okay. Um, and then am I right to assume that VWR was negative 80? Is that, or is it? Oh, there it is. Oh, okay, I see it. Okay, great, great, great. Oh, that's what I mean. VRM. Sorry. Yes, great, great, great. Okay, okay, okay. Thank you. Okay, so what I'm going to do now is like blast through all four cases. I'm going to blast through all four cases so we can talk about them. Like, right, standard Doppler effect problem. Standard Doppler effect problem. You have a source making waves. You have a receiver receiving waves. Whatever direction the waves are going from the source to the receiver, we intentionally, strategically, as problem solvers, call that positive, right? What's definitely given for all the cases is VWM and VWS, meaning, oh no, you're right, meaning what you know in advance of any Doppler effect problem is you know the velocity of the wave relative to the medium. You know that because that's the thing about waves. Every wave travels at a given and fixed constant speed relative to its medium. And I should rush to point out every wave necessarily has a medium because the medium is the collection of particles through which the wave pulse is propagating, right? Like medium is not just an accidental feature. It's the bunch of stuff that is oscillating, vibrating back and forth so that we get this whole phenomenon called a pulse or called a propagation or called crests and troughs that flow through the bunch of particles, right? So like you can't, I mean, so a wave is a wiggle. And in order to have a wiggle, you need a bunch of things wiggling in a certain way, right? So So what turns out to be amazing about waves is that once you know what the things are that are wiggling, then the wiggle necessarily flows through at a fixed speed. Okay, so what we always know, so for example, if this whole thing, if we're talking about, if the wave here is sound and the medium is air, then we know that the speed of the wave relative to the medium VWM, we know it's 340 meters. If air is at standard temperature and pressure, then we know that the wave is traveling 340 meters per second relative to the air. That like, okay, so that would be, and then like someone plays a sound, a certain note on the piano or whatever, or or beeps the horn of their car and it comes out their speaker, and they can know, they can measure, they can hear what that sound is. So that's a given. The frequency of the wave according to the source, like so FWS is a given. Now, what distinguishes the four cases from there on now, what distinguishes each of the four cases from the next is for a Doppler effect to occur, for the receiver to measure a frequency that is different from the measurement made by the source, for them to disagree on frequency, at least one of them, either the source or the receiver or both, must have velocity relative to the medium. If they're both sitting still in the medium, then there's no Doppler effect. Then the sound wave will just go from the wave, from the source to the receiver. But as long as somebody has motion relative to the medium, there will be a Doppler effect. The Doppler effect is them disagreeing on frequency. So the four cases are whether the receiver is coming in relative to the medium, or the receiver is going out, or the source is coming in, or the source is going out. So in all cases, what we're ultimately solving for, in all cases, what we're solving for is the frequency of the wave according to the receiver. That's the issue in every single, right? We know the frequency measured by the source, the frequency measured by the receiver is going to be something else. What differentiates each case is who's moving and how fast. And presumably in each one of the cases, whoever isn't moving, isn't moving. So summarizing case one, so case one, and these are not universal numbers. I'm not saying, if you looked up on the web, what is case one, you wouldn't find it. What I'm using these numbers to denote the following, like case, what I call case one is the receiver approaching the source, right? And in case one, that means the velocity of the source relative to the medium was 0, right? And the velocity of the receiver relative to the medium, so the absolute value of it, the speed of it, like Katie or somebody put in the chat, I think it was Katie, put in, was 80. But if I look at the way I'm setting up my positives and negatives, in case one, if the receiver is coming toward the source, then that means going against the direction of the wave. So case one, I designated like this, right? So this is case one. Now this is the setup for case one. Now, how I solved it, I'm just going to summarize right now. How I solved it, I always solve through the wavelength. Like the wavelength is the whole issue of the whole problem. The wavelength is the one quantity that is invariant. That is, in any Doppler effect problem, the wavelength is the one thing that the source and the receiver will both agree on. So it's the way to analyze the problem. And it reveals things about the situation. So I did this. So what I did to solve case one is I solved for the wavelength I always start by solving for the wavelength of the wave according to the source, right? And how did I do? I'm not going to anyway, the wavelength of the wave according to the source is always the speed of the wave according to the source over the frequency of the wave according to the source. And the speed of the wave according to the source is always the speed of the wave according to the medium plus the medium according to the source. So this is like a summary of what you do every single time. And you just have to think about you have to just keep all these subscripts straight and positive and negative signs straight. But in the case where we did this Monday, we found it was 340 plus 0 over 440. Oh, wait. Oh, sorry. Yes. Okay. I see the thing in the chat. The answer is yes. And I'll be specific in a second. Yes. Hold on. Um, okay, so wait, okay, I'll look in the chat. I think I know what the question. Yeah, right. So, so this is now me hopefully re-explaining or reviewing or so, but right, I'm doing the condensed version right now. So someone's asking in the chat, for an exam, would we have to explain how we derived V equals lambda F when solving a Doppler effect problem? Oh, actually, maybe I misread the question. For an exam, you would certainly have to derive what I just wrote here, that lambda equals V over F. You at least certainly have to take a step back and show that that came from V equals lambda F. Now, V equals lambda F. Would you have to derive that on an exam? Well, as usual, my most conservative answer is the very first case you do, the very first exercise of this that you do, it would be great, certainly, to back up. And yes, remind the viewers at home that this came from this. Yes, maybe one time. Now, depending on which problems you choose in the exam, you might have already done this in a different problem, maybe, but somewhere you want to show, yes, that um, uh, yes, you want to show it from V equals omega over K, and what's omega is I'm really losing my mind. That omega is radians per second, and K is radians per meter. So the radians cancel out and you get meters per second. Yes, like one time you want to do that, but then once you've done it, then you're good to go from then on. So that's a fair question. Um, so what I've done is I've gotten the wavelength according to the source. Then I go and say, okay, well, the wavelength according to the source must be the same as the wavelength according to the receiver. So then I use the wavelength according to the receiver to say, okay, so notice, oh, you're welcome. You're welcome. So again, I'm being clearly I'm being a little bit this is supposed to be a somewhat brief, but maybe it's like underly brief summary of what we did on Wednesday. You show the steps, you drag this out a little bit more, but just notice that the pattern here is I'm getting the wavelength, I'm using the velocity and the frequency to get the wavelength according to the source. Then I'm going over to the receiver, taking that wavelength and using it with the velocity over at the receiver to get the frequency of the receiver. So what I am doing is going in a circle. Please understand that. I'm first using V and F to get lambda. I'm keeping the lambda. I'm going over to the receiver, and then I'm using lambda and V to get F. So if you really think about it, once you get that that's what I'm doing, you may realize, or you may think for a second, wait, why doesn't he just end up with the same answer that he started with? And the reason is, if you look closely, the V is what's driving this train. The V changes from source to receiver, right? In all cases, the way I get V is I use relativity. I say V of, like, look, like right up here, V of WS. How do I get it? Like, and I'm also just trying to alert you to the sort of common error or the common thing that people miss is VWS means the velocity of the wave according to the source. In English, conceptually, what's happening here is the velocity of the wave according to the source is not the number that you're given at the beginning of the Doppler effect. Like, it's easy to think that it is, but it's not. What you know at the beginning of a Doppler effect problem, what nature knows, what the world knows, is the velocity of the wave according to the medium. Like, that's what you always know. You know the speed of sound in air. Then what the Doppler effect is really saying and asking you to solve for is, okay, if the speed of sound is always 340 in air, that doesn't mean that it's 340 to all people at all times. It means it's 340 to air. So it means that anybody standing still in air will observe 340. But anybody who's moving through air, relativity, from their perspective, air is moving past them. So anybody who's moving through the air, it's like a box of air is carrying the sound to them and moving toward them and moving away from them, right? So they won't agree. They won't observe the speed of sound to be 340. It'd be something else. And so see, in this case, when you look at the velocity, so you always have to do velocity of wave according to source equals velocity of wave according to medium plus velocity of medium according to source, right? That's the relativity thing. That's the ABC thing, from last semester that takes some getting used to. But what I'm trying to emphasize here, and I will go on, I'm trying to emphasize that you do that step every time. And it's like physics always, you do that step, even in the cases where it doesn't seem necessary to do that step, even in the cases where one of the numbers you're adding is a 0. So you almost feel like you're wasting your time or something like that. But you're doing it to reinforce that it's true every single time, whether there's a 0 or not. So it makes the habit. So like up here in the middle of the page where I say lambda WS equals VWS over FWS, then I pause and go, oh, VWS, wait, I don't actually literally know that. I know it's VWM plus VMS. I've got to add them. But the fact is VMS, that means velocity of medium relative to source. Well, in this one case, the source is just sitting there in the medium. So the medium is therefore, sitting there to the source. So in this case, that's 0. Okay, but in 2 out of the 4 cases, it won't be, is the point, right? So that's why you set this up every time. So it's 0. So I go 340 plus 0, 440, right? Because the source is not moving in this case. Then I get down to the receiver and I do the same habit. When I get down to the receiver, I say VWR over lambda WR. I'm down here now. VWR over lambda WR. What is VWR? See, now I got to pause. I had to pause the other time, but now it really matters. The velocity of the wave relative to the receiver is not 340. In other words, the receiver does not, from her perspective, does not measure a 340 wave. The wave, the sound is going at 340 through the air molecules, but she's running into the air molecules. Therefore, the air molecules are running into her, right? So, and now here's okay, again, I'm rabbit holing, but so I ended up saying 340 plus 80. Now let's be why did I say plus? Especially if you're paying attention, you notice up here, I used a negative sign. Wait, what's going on? How am I making these decisions? If you're careful and consistent, they all decide themselves for you. What I'm saying is this: the velocity of the receiver relative to the medium is 80. The receiver, is negative 80. I'm sorry. She is running through the medium at negative 80. Why did I say negative? Because the wave is coming this way. And whichever way the wave goes, we always call positive, right? I mean, if you look at the wave is going left to right in my picture. Therefore, left to right is called positive. But now in this case that we're doing, the receiver is running in toward the wave. So she's going negatively. VRM, velocity of receiver relative to medium, is negative 80, right? But then what this thing is asking for, oh, see, I skipped this. I probably shouldn't have skipped. What I'm doing here in the physics, I'm saying lambda WS equals VWS over FWS. So I'm saying VWS is VWM plus VMS. It's a lot of subscripts. But it's all that same pattern. It's VAB plus VBC equals VAC. It looks like transitivity or whatever. VWM plus VMS is what I want here in the numerator of this fraction. And I'm sorry, I'm not S's, R's for this. I mean, that's all correct, but I'm talking about R's right now, receivers. So I'm also freaking out the dog. These are all ours. So, oh my God. VWM plus VMR is what I want specifically. Like, notice A, B, B, C, WM, MR, like that. It's not arbitrary. But I want MR. I want MR. But what I know is RM. I know that the receiver is going into the wave negatively. So VMR is positive 80. I'm dwelling on this. I'm not going to do it every single time, but that's the thought process you have to do every time. Like, if, right, this is again relativity. If she's going through the medium at negative 80, then the medium is coming past her at positive 80. What do I mean by positive? I mean the same direction as the wave is traveling. So she's running. What is she experiencing? She's experiencing a big wind blast. She's experiencing sound that's coming toward her at 340 in air that's coming toward her at 80. So the sound is coming to her much faster than it was leaving the source. That's so that plus that's so in other words, sometimes this plus will be a minus. You have to think these parts through. But you just follow the letters, what the subscripts are telling you to do. So anyway, so you get, but really stop me if that's not, because we're going to do that same thing every time, but I'm not going to explain it every time. So please stop me if it's not clear. But so and so the summary of all that is, so notice, all I did was I got wavelength by putting V over F, and then I go over to the receiver and I get F by putting V over lambda. It like literally looks like I'm just running in a circle algebraically, but I'm not running in a circle because every single time I do it, in every single case, the V in one case will be 340 plus 0, and in the other case will be 340 plus something. In which case it is, depends on which it is. And I might add, in two of the cases, it'll be a negative sign up there, and in two it won't, if that makes sense. So that's what you're paying attention to. All right, so on the next page, therefore, so this is all a big summary of what we already did, I know. Fire myself. So in the end of the day, so this is all case one still. Case one continued. So FWR equals 340 plus 80 all over 0.773. It's approximate. Okay, so what we found, I'm pretty sure, what we found in class on Wednesday was we got 543 hertz. Now, that was case one. What I'm going to do now is quickly, I'm going to do the same method, but without talking it all the way through for all the other three cases. And so this is partly so you could see if you did your homework right, and we also just whatever. All right, so case two, to cut to the chase. So case two, what was given now case two, this is the receiver recedes. Like it's still the receiver that's moving through the air, but it's the receiver's moving back. So we're going to, yeah. Oh, okay. Okay. I was literally just going to say that, I think. Wait, hold on. Wait, yeah. There's something in the private chat. Right. Okay. So someone just wrote in that I was literally about, very good. I was about to address this. Someone just wrote in the private chat. So they say, so will case one always yield a frequency of wave relative to receiver that is greater than the frequency of the wave relative to the source? Like, is that a pattern we can be certain of to check our work? But beautiful question. Also, I might add beautifully phrased. Like, they definitely said it all exactly right, and it is a mouthful to say. So the answer is, okay, the short answer is yes, as long as we all understand, and it's important, it's not even, I mean, that great point. The answer is yes, as long as we all understand I'm doing these cases in a certain order, calling them case one, case two, case three. I mean, and I like that order. And sure, I tend to probably to do them in that order. I tend to, even on exams. But I'll even be honest, like on the exam, I don't necessarily ask you about all four cases. I usually ask you to compare two key cases. You'll see which ones when I'm done. So the one thing I urge you to realize about spot checking, stuff like that, is don't get too bogged down in like which case is first or which is second or something like that, or what's called case one or case two. But what you definitely can rely on 100%, and not only can you, but it's very good to take note of, yes, when the receiver is moving toward the source, for sure, the receiver will measure a higher frequency than the source will. That is a guarantee. And so now in case, when I move to what I'm calling case two, if I now do the receiver moving back, I absolutely should expect that the received frequency will be not only lower than that, but lower than the source frequency. We're going to get a number now, if we're doing this right, we're going to get a number that's lower than 440. And yes, you can bank on that. I'll even go so far as to say, if you're really trying to get a hold of this, I could tell you right now, you notice that the frequency when we were running in was about 103 hertz higher than 440. Like 440 is the source frequency. We got 543 as the received. Yeah, so that's like 103 higher. I think it's a very good spot check or prediction. We're gonna get, if we do this, if we do this right, we're gonna get 103 hertz lower than 440, i.e. like three, oh my God, like 297. What? I can't even do math anymore. Like 337 or so. Like there's rounding that goes on, but basically 337 we should get when we're on our way out. Absolutely. And now that's for case one and case two. I'll talk about that's for the receiver coming out or the receiver coming in. And yes, and the way to understand that is not a coincidence. And yes, you can bank on it because like the physical thing that's going on here, the concept that's going on is if you were at Coney Island or Far Rockaway, I mean, if you're at the beach and there's like a boat out there making waves or something making waves and the waves are coming in, the boat or the whatever or the moon might be making waves that are coming in like one every minute, right? Or two every minute. So like a frequency of two every minute, right? And if you just stand at the beach, then they'll hit you two every minute. But if you're running in toward the water, even if they're made to come out, even if the boat measures them as coming out as two every minute, if you're running it to meet them, you are certainly going to intersect with those waves more often than two every minute, right? Because they're coming at two every minute, but one hits you, but then you like are running forward. So you're helping out the whole situation. You're getting closer and closer to the next wave even faster than it would have if you just stood there waiting for it. So for sure, whenever frequency goes in to source, the receiver gets a higher frequency. And when the receiver goes away from the source, you get a lower frequency. And it's such an important question. And I hope, and maybe they'll tell me in the chat if I made it clear, I'm going to go even an extra further thing and say, since we're about to get all the four cases, I hope, yes, conceptually, qualitatively, that is also true for case three and case four. As long as things are coming together, the received frequency will be higher, will be higher than the source frequency. So even if that boat is coming in toward you while it makes the waves, what we're going to find when we do the math here is that we'll get a received frequency that's higher than the source frequency if stuff is coming in. And if stuff is going out, we'll get a lower frequency. Yes, you not only can direct chat person and everybody, not only can you bank on that if you're doing this for an exam, but you like should. And you can even talk about it. It's like absolutely physically what's going on. Okay, makes sense. Okay, cool. Okay, so yeah, I'm like predicting, thanks for that question. I'm like predicting, we're going to do this quicker and quicker. I'm predicting we're going to get like 103, we're going to get like 337. I keep saying that. Yeah, like 337 or so for the hertz. So, but I'm going to do it a little more quickly now, right? What am I going to do? I'm going to go to brown because brown seems to be the color of today. Sorry. So I go wavelength coordinate source equals, sorry. So now I'm going to start trying to talk less and just do it and do fewer steps. So that means I'm trying to bore you less and drag you out less, but it doesn't mean you shouldn't stop and ask questions in the chat. Like, honestly, I'm just going to start to try to go a little bit on automatic pilot here. It doesn't mean you shouldn't stop me. It means I'm not stopping me. Okay, so okay, I'll go to the next page. So notice so far what I'm saying is if I go to the next case, first I solve the wavelength according to the source. Notice it's the exact same procedure, but also in this case, exactly the same numbers. Like I mean, whether the receiver is coming out or coming in doesn't affect the wavelength. The wavelength, I ended up getting the exact same number as before for case one. Not a surprise. That's also, you can spot check that. But now I go to the other page. So and yes, if you were doing an exam, you would explain this more. You wouldn't just like write it out the way I am, but whatever. I'll even. Oh, did I say? Oh, and I'm sorry. I'm gonna go back. I should have said, so the get in this case, I should have said this. In case two, where the receiver recedes, what's changed now in terms of the givens? What's changed is the velocity of the source relative to the medium is still zero, just like case one. But now the velocity of the receiver, according to the medium, is now positive 80, right? Because now it's going back. It's going in the same direction as the wave. So the velocity of the receiver, according to the medium, is 80. Therefore, just to be clear, if right, so we flip the negative sign, and I want you to know, I know that after a while, it all seems like a bunch of negative signs, and it all just seems like arbitrary decisions that I'm making and stuff. But this negative sign that I just put on the 80, it's not an arbitrary decision. Like, just please remember, this is all, everything we're doing is coming from relativity, and relativity, GPR form number 4 is all summarized like right here at the front, and like we did it last time. I'm not like, the whole idea is that in a one object case, every object moves not at all to itself. It's all the Minecraft thing, the Pixelmon thing, really, right? Like any object to itself is zero, but any object to something else is the opposite of what the something else is to it, right? VAB equals negative VBA is the thing that I'm saying. Every time I flip a negative sign, it's because if the velocity of the receiver relative to the medium is given as negative 80, as positive 80, then the velocity of the medium relative to the receiver is given as negative 80. And how do I know that what I wanted was the velocity of the medium relative to the receiver? Because of this third statement, because of VAC equals VAB plus VBC. It doesn't say VAC equals VAB plus VCB. You see what I'm like? What I'm just trying to emphasize is this literally is all a logical progression. it seems like you have to memorize all of these minus signs and all of this stuff, but you don't if you're really taking it seriously what relativity means. Okay. And honestly, sidebar, I think with that other equation from the lab, I think there you have to memorize a bunch of cases of like, okay, with this case, we do a positive sign here. And if it's that case, you do a negative. Now, look, and again, some people like that better. I'm not here to judge, but I am here to show you the concepts of physics. So here's the concepts. Okay. Anyway, I am here to judge. Who are we kidding? No. Okay. So back to this. So all of that goes over 440. So, oh, no, all of that goes over 0.773. Right, so it's the same procedure as case one, only we have a negative sign in there now. Instead of right. And so again, in this case, I said I wasn't going to talk as much. I always say that. It's the kind of thing that talky people say. Right, and so you get, as predicted, this. Okay. So that's case three. Sorry, no, it's not. That's case two, and it's 1 o'clock. Okay, well, all right. Again, stop me. So in the end of the day, the one big difference between the two cases was just literally that negative sign. It's in the same, like, that's the whole difference. Again, I don't think that's a thing to memorize. I think it makes sense. I'm picturing now if the receiver's running away, that means that she is running away from sound, from air that is carrying sound toward her. So the sound does. So if you ask the receiver, what's the speed of sound? She would say, well, to air, I guess it's always 340, but but not to me. To me, it's a lot slower because the air is dragging its feet. So, okay. So now we'll go to case three. Now things get a little more interesting. Case three, first of all, now is, and again, don't memorize the numbers, but by case three, I mean the source approaching. And here what's given, still all the same note and all that, but here now the receiver is sitting still in the air, but the source, if it's the source is approaching, we're still on purpose using that number 80, but if the source is approaching, it's approaching. So it's going in the same direction as the wave. The wave's going left to right. We call that positive. If the source is approaching the receiver, the source is like running after the wave, so to speak. So it's positive. So the source relative to the medium is plus 80 meters per second, right? Okay, so now we do the same procedure as every single time. So I say, okay, what's the wavelength according to the source? Well, it is the velocity of the wave according to the source over the frequency of the wave according to the source. What's the velocity of the wave? Oh, I said I wasn't going to talk. Right, and you see the pattern. I said I wasn't going to talk. Wm plus ms equals ws. Like, it's not A, B, and C, but it's the same arrangement as A, B, and C. And what is all that? If you're ever trying to like memorize that or get that straight, all of that is the velocity of u relative to the subway plus the velocity of the subway relative to the streets is the velocity of u relative to the streets. That's why you take subways, right? Like that's what we're saying here. So like the sound is riding the air train, so to speak. Everybody get on board. Woo woo. Okay. So, all right. So now velocity of wave relative to source equals velocity of wave relative to medium plus velocity of medium relative to source. Well, velocity of wave relative to medium is 340 as always. Velocity of medium relative to source is now not zero. Like now we're getting to a case where we don't just obviously have a zero up there in the first step. We're going to have a zero down there in the last step, but we do, right? It's the same logic, but it's a question of where the zeros end up and where the negative signs end up. And it's not arbitrary. I look at that VMS. What is VMS? VMS has to be the opposite of VSM. And I was given a VSM that wasn't 0, right? The source is moving at 80 relative to the medium. Therefore, the medium is moving at negative 80 relative to the source, right? That's the logic of this. And that's all over 440.
I have a wild question.
Yes, please. Yes.
So, because I was doing this before, and I was just like, why are my numbers like not adding up? Like my source approaches was lower instead of my source moves away, and now I see why. But before we were doing case 1 and case 2, it was velocity source to medium, and we didn't like inverse the source to medium velocity. Why do we do that now?
Wait. I'm confused. Wait. I love the question. I totally got 75% of it, but then, all right, in case 1 and 2, we did plus. I'm claiming that we're doing plus VMS in every single case. Like what I'm claiming is that no matter what, we're always adding the velocity of the medium relative to the source. I'm saying in some cases it's 0, like in case 1 and 2, it was 0 because the source was. In all cases, we're adding VMS. And in all cases, we're saying that VMS is the negative of VSM. And in all cases, we're saying that VSM is actually the thing that's given. Like what we know is what the source is doing in the air. What we need always is what the air is doing to the source. So in every single case, we're actually putting a negative sign on whatever was given to us and adding that. In all cases, we're putting a negative sign on whatever was given to us, whether what was given was positive or negative. We're adding that. But in the first 2 cases, it happened that we were putting a negative sign on 0. So we got negative 0, which is 0. I mean, I'm not sure if is that what you're like.
Oh, I might have just wrote it down incorrectly because I was using velocity SM, and when it was 0, it was 0, negative 0, positive 0. That didn't affect my answer.
Oh, right. See, and that okay. I think I understand what you're saying. Yeah, what I'm writing down, you maybe you did like I'm not that may be that you might have just written
It's
it down.
thoroughly possible that could have happened.
Okay. So, but no, but I'm really glad you're stopping me on this and asking. Like, you're definitely not the only one. Right. One of the reasons I keep dragging this out for everybody is because of that 0. There's so many reasons not to actually see what's going on because the 0 like disguises like all of these subtleties that are happening. Like, right. Like, first of all, because of the 0, like a lot of people wouldn't even realize that we're adding anything. So you realize we were adding something. But yes, it's possible that you thought we were adding like the opposite of what we were adding. And right, the 0 just totally masks that. So yeah, I'm saying, and so I'm saying it all goes back. It all goes back to where to go to this thing, It all goes back to AB plus BC equals AC, like whatever those letters stand for. Like it's like that transitivity is always what we're doing, and it actually matters, especially when the numbers aren't 0. So yeah, I'm saying literally every single time when we're looking at the source, every single whatever we're looking at, if we're looking at the source, yeah, here we are. We want WS, so we get it by saying WM plus MS. And MS necessarily is not what we were given. We were given SM. And yeah, I think we're on the same. So yeah, I think maybe you just wrote it down wrong or whatever. But yeah, so I promise. But the other reason it's good that Katie asked that. I mean, even if, and I'll look in the chat if like hopefully it's clear to her now. Like even if she just made a mistake writing it down, it's exactly like the kind of thing I'm trying to address here because it's super, super common. But also, I'm just trying to emphasize to everybody, this all looks like like a huge bunch of weird rules to memorize until you see what's happening. And then you realize it's like one rule that we're memorizing, which is the relativity rule. I'm going to look in the chat in a second. And it looks like we keep changing our mind every time of what to do. But And so it's good that everybody's like really scrutinizing these details because we're really honestly not. We're doing the same logic every single time. But it can get masked whenever, but there's always a zero somewhere, and where the zero is changes. So it can really fool you until you do all four cases. Okay, I'm just gonna look in the chat. Maybe that's Katie saying that she gets in a. Oh yeah, okay, cool. Thank you. All right, awesome. Okay. And that's points, points, points. Okay. And I have a lot of points to catch up to give you guys. I know that I'm totally behind, but they're not lost. Okay. So anyway, so now in the end of the day, this says this. I'm looking at the time too. Okay. So here now, we're not done. One thing, we're going to get an answer in a second. Just one thing to pause. Notice here now, like, so now this velocity, like the logic of it is now the source is running it towards the receiver. So the source is sending out this sound in the air, but then like running into the air while she or he is making the sound. So this is just this fact that we're now saying the velocity of sound relative to the source is 260. Like it's just the same logic we did before with the receiver, but it's actually particularly interesting that it's happening to the source now, because this is where right here, in a way, I mean, I will get to the end, but right here, the fact that there's a non 340 number in the numerator there is really showing what's different about waves from particles. Because from like a baseball, you can't do this with a baseball. The thing I just want to emphasize is like when you shout, the sound comes out of your mouth and immediately like gets like, it's only because there's air outside your mouth that the sound can travel at all. So immediately from the moment the sound comes out of your mouth, the air dictates what's happening to that sound. Like immediately when it comes out of your mouth, it will be going 340 relative to the air, no matter what you're doing in the air, right? That's not what baseballs do. You throw a baseball and it comes out of your hand at the speed that's dictated by your hand, right? So if you throw a baseball at 100 miles an hour, it's 100 miles an hour relative to you, no matter what you're doing in the air. Even if you're on a train going 200 miles an hour through the air and you throw the baseball off, it will get the speed of your hand plus the speed of the train. It'll go, so someone standing on the platform will see the baseball go 300 miles an hour, like for real. Not just see it, but like measure it. But that's not what waves do. Waves come, so what I'm really trying to say, I'll move on, but like if you threw a baseball off a moving train, no matter how fast the train's going, the train is not going to have you catch up to the baseball. Right? Like while the baseball is moving, I mean, before it like hits the ground or something, while the baseball is moving, I don't care how fast that train's going. The baseball, you're not going to like slam your face into the baseball that you just threw, because even if you're going 500 miles an hour, the baseball gets that 500 also, right? So if you throw a 100-mile-an-hour pitch in an hour, the baseball would be 100 miles ahead of you, like if it didn't hit anything, or, if you're like really high up, whatever, if you go to throw a 60-mile-an-hour pitch, then in 1 second, the baseball is a mile ahead of you, no matter how fast the train is that you're standing on. But that is not true of waves. That is not true of waves. If you make a sound and it comes out at 340 and you're in an airplane, if the airplane is now going 340, like what this is saying right here, when you look at that number, the 260, it's saying that the sound is actually not going that fast relative to the thing that just made it. So if you bring it all the way to the extreme, say the source was moving at 340, like say it's an airplane that's a supersonic jet that literally can fly at the speed at which sound flies through air, well, then a very interesting thing happens, right? If an airplane makes a sound and the sound's going through the air, but then the airplane like accelerates or whatever, or already is going at 340, that means relative to the plane, the sound is going zero. Like that's what this math is saying. And it is true. And it is true of sound, not true of baseballs. So if you're picturing what I'm asking you to picture, I'm saying an airplane that's continually sending out vibrations in the air, oscillations in the air. If the airplane is moving as fast as those oscillations are, then the airplane will stay with the sound. It will. what is sound? It's a bunch of high pressure pockets of air molecules, like, right? Like sound is air molecules moving together and then apart. I mean, together and then apart, and then together and then apart. So like high pressure, low pressure, high pressure, low pressure. So you have all of these high pressure, low pressure, high pressure, low pressure, like pockets of air molecules that are moving along, but right next to an airplane that's moving along. So the airplane will be in a big wall of sound. And if it goes any faster than that, it will break through that wall of sound and be on the other side of it. The airplane can catch up to and pass its own sound in a way that you could never do with baseballs. I hope you see what I'm saying. And you know what I'm saying. If the airplane does do that, if it catches up to and breaks through its own wall of sound, that's a sonic boom. And that's why they exist. And that's why there's no such thing as a baseball boom. You literally can't do that, but you could do it with any wave at all. All right, anyway, so that's what's happening. So looking at the time, okay, 13 minutes. So the wavelength is now 0.590. Notice that's that's not 0.77. I'll talk more about that at the end to whatever extent I have time. But notice now, this wavelength is now a new, well, should I say, yeah, I'll just say quickly. So what's happening now is the source is making waves that are coming out, but the source is like running from wave to wave as it makes them. So it throws out a wave crest and then it keeps going forward. So then by the time it throws out the next crest, it's already a little bit closer to the first crest than it would have been if it just stood still. So the crests are closer together. You see that the wavelength here is not 0.77 now in case 3. It's 0.59. The wavelengths got compressed. Now you might say, wait, I thought the wavelength's always supposed to be the same. If you're thinking that at all, you are. What's supposed to be the same is that this wavelength, whatever it is, I'm not saying it's the same all the way through all cases in all life. I'm saying whatever this wavelength is will be agreed on by both the source and the receiver. So I'm saying this new wave, so I'm saying do take note. We're in case 3 now. What just happened was the wavelength got compressed. It's not the same as case 1 or case 2, but it most certainly is the same whether you're the source or the receiver. So we go to the other page and we just continue the same method. We say, okay, now FWR must equal VWR over wavelength WR. VWR must equal, okay. Okay. Must equal VWM plus VMR. And notice too, I'm writing this back to the Katie thing. I'm saying VWM plus VMR, and I'm saying it unthinkingly. Like I'm not thinking ahead of myself. I don't know whether it's a negative or I don't know what I'm doing. I'm just writing down the pattern. VWM plus VMR. And then I just do one step at a time, one step over VWR. Okay. So VWM is 340. Now VMR, the medium according to the receiver, well, VMR must be the opposite of VRM. That's how right? And VRM was given, but VRM was given a 0. See, so the 0 now is at this part of the problem. Like, because the receiver is just standing there in the air. So all of that over, over 0.5, whatever we said, 0.590. Yeah. So for this one, we get 576 hertz. Okay, so this is case 3. We'll quickly do case 4. Just note very quickly, case 3. So this is the source moving in. So on the one hand, like, case 1, just like case 1, this number is higher than 440, just like the direct chat person asked like 20 minutes ago. Like, because the source is moving in, so the frequency is higher than the source frequency. The receive frequency is higher than the source frequency. 576 is higher than 440. But they're not the same number. Note that. That's why we're dragging this out. That's why 576 is not the same thing as whatever. What was the other one we got? Is not the same thing as 543. And that's not rounding. I mean, if we got like 544 or something, that might be one thing, but 576 is not the same thing as 5. So just note that so case 1 and case 3 qualitatively have the same effect of being bigger than, but they don't yield the same result. Note, put that in your pocket for a second. We'll just quickly do. Okay, now if I'm going to do case 4, hopefully I won't talk this one. I'll do it really. If you're seeing the pattern, we're going to have a 0 in the same place as case 3, but where we put an 80 in case 3, there's going to be a negative sign this time, or vice versa. And presumably this answer will be like 136 hertz below 440. If you see the right, we'll see. So case 4, we'll do it quickly. So now the source is moving back. So now it's negative 80. And I should have just written this from the start. So if the source is moving back at negative 80, then the medium is moving forward relative to the source at positive 80, right? So now we do the wavelength and all that stuff. So now really this is a plus positive 80. So because now the source is running back. So she's separating from the wave. So the wave is going forward through the air at 340, but it's additionally, she's going away from it at 80. So it's every second it's separated by, 420. So now the wavelength is huge. It's much bigger. It's bigger than 0.5, whatever, and it's 0.59, and it's much bigger, and it's bigger than 0.773. The way, right? Because now every time she throws out a wave crest, she runs back. So by the time she throws out the next wave crest, she's even farther behind than she would have been if she were just standing still. So the wavelength is stretched out now, and it really is, right? But that doesn't mean they're going to disagree on it. They're both going to agree. So it's a different wavelength. So you got to be really careful. I'm saying that the wavelength is the thing to watch because in any given case, everybody will agree on the wavelength. That does not mean that the wavelength is the same from case to case. It means within a case, everybody agrees on it. Honestly, in physics, that's the difference between saying something is constant versus something is invariant. The wavelength is invariant. It doesn't mean it can never change. It means whatever it is, it doesn't matter what frame of reference you're in, you'll still agree on it, okay? So the wavelength is invariant. So now we say, okay, so the wavelength is the same to everybody. So it equals whatever we just said, 0.954 approximately. So the frequency of the wave according to the receiver is the velocity of the wave according to the receiver over the wavelength of the wave according to the receiver, which is so we get 340 plus 0 over 0.54. So this time we get Okay. Okay, we have 4 minutes. So first of all, this is how you do it, right? I dragged out more than I wanted, but hopefully when you see, like you can see this thing, you have to practice. And I'm glad from the questions I got from a couple of people, clearly they did try the homework and they were practicing it. Okay, so they hit a little stumble thing. That's why we're here. But you can see this is detailed enough that you can't fake it without, you got to practice it a couple of times. And you can't just practice it with that equation from the lab, because the equation from the lab, even if you like it more, it never reveals anything about the wavelength. And what I'm trying to focus your attention on here is what's happening with the wavelength. So number one, practice. Okay. Number two, and I know there's 3 minutes left. Number two, notice now, let's stand back. What's happening here? What's happening here is, on the one hand, it's all a big illustration of relativity, of how velocity is a relation between two objects. It is not a property of one object. And so two people can disagree on a velocity, and they can disagree on all the implications that come from velocity, and they'd both be right. Like, that's the thing in physics, right? No one frame of reference is more legitimate or correct than another. That's what's happening here. So one person ends up hearing one note, the other person hears the other note, and they're both right. And if they recorded them on iPhones and then played them, they'd be different notes. But what's also happening here is that so it's relativity. It's if the Earth observes the sun going to the west at 65,000 miles an hour, the sun observes the east, observes the Earth going to the east at 65,000 miles an hour. It's perspective, right? But this is relativity being applied to waves. So it's illustrating some really interesting features of waves that are coming out that don't apply to particles. And one of the key features is this. According to relativity, whether I move to you or you move to me, that should be the same thing, right? But here, if you do all the 4 cases, you see that if the receiver moves toward the source, qualitatively, they get the same Doppler effect as if the source moves to the receiver. But numerically, quantitatively, they don't, right? The answer that ends up happening, the difference in the notes, is different if the receiver's coming in versus whether the source is coming in. And if you're really following all this, that's actually noteworthy, because if you're following the logic of relativity, you would be right to be vaguely confused and go like, wait a minute, I would have thought, like, I mean, whether I'm running into the boat or like whatever, if I'm running into the speaker or the speaker's running it to me, I thought the whole thing of relativity is, who cares? Like, shouldn't the numbers be the same? If you if you think that at all, you're on the right track. But here's the thing. What this all shows is that with a wave, there's a medium, and the medium is real. The medium is a frame of reference. So it's not about receiver to source, source to receiver. It's about receiver to medium equals medium to receiver, and source to medium equals medium to source. There's a third frame of reference here called the medium that's making all the difference. So much so that when the source sits still in that medium and the receiver comes to it, what happens is, and you might want to write this down. I know I'm saying this quickly, but it's super helpful for the final exam. I'm sorry if I'm saying it quickly. You can remind me on Monday and maybe I'll say it again. But here's the key. When the source sits still, and I know it's 1:30, I'm just going to say this and then goodbye, or if you have to go, okay, someone just did, goodbye. But when the source sits still in the medium, the source sends out an expected customary wavelength, but the receiver receives it at an uncustomary, unexpected speed. However, when the source is moving through the medium, the source sends out an uncustomary wavelength, an unexpected wavelength that gets received at an expected speed. In other words, in 2 out of the 3 cases, we're actually messing with the wavelength right from the get-go. We're sending a different wave, right? Because you can literally catch up to your own wave or run away from your own wave in a way that you cannot with baseballs. So really, I know I'm keeping you over. I'll try to say this again, but when you see the problem that is usually on the final exam about this, what it asks you to do is like walk through a couple of these cases and show how it makes a difference whether the source is moving or not. And it asks you to redo the same thing with baseballs and see how with baseball, or like little electrons, with particles, Particles would also create a Doppler effect, but the Doppler effect would be the same whether the source was moving or the receiver was moving. The Doppler shift would be the same either way because there's no medium involved. So this is actually a way we can tell the difference between particles and waves, is whether the source motion case differs from the receiver motion case. It's a very subtle point, but it is absolutely a litmus test for whether a bunch of stuff actually is a bunch of stuff or just ripples through a medium. Okay, that's enough for today. Thank you for being so patient. Okay, have a great day. Yes, have a great day. Thank you. Okay. So yes, have a good day. And wait, I'm looking when I'm stopping recording. I'm looking at the gym.